Alright, this lecture is our second lecture on the topic of recursion. So today I'm going to show you some additional examples of recursion, including the way you make the image that's shown here on the intro slide. As a review, recall that recursion is whenever a method calls itself. And so it's a new way of sort of thinking about a problem and breaking it up and trying to algorithmically solve some problem you've got. And it's a very powerful paradigm in computer science. And last time we saw some various things you could do with it. We saw sort of hello world with recursion, which was the factorial. Not terribly useful, but it's the simplest example of using recursion. We looked at actually a very useful and commonly used algorithm called binary search, and we saw a recursive solution for that. Then we also saw how to draw some pretty graphics. We looked at the H-tree program that drew recursive H's, and then we also looked at calculating Fibonacci numbers and how sometimes recursion isn't the best solution. So we saw the calculation of Fibonacci numbers using a recursive algorithm was actually really slow. Today I'm going to show you some additional examples of recursion. I'm going to tell you about the greatest common divisor algorithm. We'll look at Brownian motion, and then finally we'll look at how to efficiently sort things. Let's start off with the GCD, greatest common divisor. The problem here is to find the largest integer that evenly divides two other integers, p and we'll call those two other integers p and q, and we'll assume p is greater than q. And if somebody asks you what's the greatest common divisor of 4032 and 1272, you'd say 24. And how did you get to the 24? Well, you computed the prime factorization of the two numbers. You figured what combination of primes multiplied together gets you that number. And in the case of 4032, it's 2 to the 6 times 3 squared times 7 to the first. And 1272 you can see as well. And the greatest common divisor uses the minimum of each of those shared prime factorization. So it uses 3 of the 2's and 1 of the 3's, and if you multiply that out you get a greatest common divisor of 24. Applications of GCD would be, for example, simplifying fractions. Another application, it's used in cryptography in the RSA crypto algorithm, and this is the algorithm that's used to secure internet commerce. So whenever you buy something online, it's using RSA cryptography, and in that problem space they need to be able to quickly and efficiently compute GCDs. You might stop for a second and try and think, well, how would I solve the GCD problem with a computer? What kind of algorithm could I come up with? And if you just think for a second, you might come up with a very simple way to do it, right? You could start with in this case, say you could start with 4031 and work your way down and try and find a number that's evenly divides both these numbers. And once you find that, then you can stop. All right, or maybe you should actually start at like 1272 and work your way down. That's a very simple algorithm, but it's also going to require a lot of time. If these numbers are really big, you'd have to test a lot of numbers to try and find one that evenly divides. You'd find it eventually, and it'd be a very simple algorithm. And I'm going to show you a very simple and very efficient algorithm. And this algorithm is probably the oldest algorithm in the world, developed by Euclid in 3000 BC. And how this algorithm computes GCD is to make it smaller every time. If you're trying to compute the GCD of P and Q, well, the GCD of that is actually the GCD of Q and the remainder of P divided by Q. And so since Q is smaller than P, and then obviously P, the remainder of P divided by Q is also going to be strictly less than Q as well. So you've made your problem smaller in a some big step rather than going one at a time down through the numbers. And here's a concrete example using the two numbers I just showed you. The first step of the algorithm, you take the second number and that becomes the first number. So the the q becomes the p. And what do we put in the second slot? We put 216. And why 216? Well, that's because that's a remainder. We can fit 3 1272s into 4032 with a remainder of 216. You take the algorithm, you do the step again. The q becomes the p, we get 216, and then we get 192 remainder. And to do it again, you get a 192 with a 24 remainder, and now you have a 24 and a 0 remainder, and now you've hit your base case. Q equals 0, therefore the GCD is 24, which is the correct answer. This diagram kind of shows the intuition of why this works. So let's say we've got a P, let's say X is our greatest common divisor, and P is 8 times X and Q is 3 times X. Well, if X is the greatest common divisor of both P and Q, you could look at this diagram and say, well, P is divided up into, some number of X's, and the X's have to evenly, fill that space of the P bar. Q also is an even multiple of X. There's some number of Q's. In this case, there's 2 of them. Since Q is less than P, there's going to be at least one Q that fits into the P. All right, and then we're going to have the leftovers. This is the remainder of dividing P by Q, but that also has to be evenly divisible by this X. All right, because it's occupying the same kind of horizontal space, and therefore, instead of looking for the GCD of P and Q, all right, X is still a GCD. It's a GCD of Q and P mod Q, and that's the reduction step in Euclid's algorithm. So that's our first example. Oh yes, and here's the if you want to see it in code, there it is, dead simple. Here is the recursive solution to finding the GCD in Java, and it just literally implements Euclid's algorithm in a few lines of code. Next problem I'm going to show you that uses recursion is Brownian motion. This is a physical process that models many natural phenomenon. For example, prices of stocks. You can also use it to model mountains and clouds, and people use it to generate really cool landscapes in computer graphics. I'll show you an example in a few slides. Here are some example runs of you could imagine these graphs represent maybe the price of stock throughout the year, and they have different variability depending on maybe what kind of stock it is. To simulate Brownian motion, we're going to use the midpoint displacement method, and what we're going to have is we're going to have an interval from x0, y0 to x1, y1, and now there's a line that directly connects those, but what we're going to do is we're going to perturb it, and this middle point is going to perturb that line by a plus or a minus. It's going to perturb it by a delta, where that delta could be positive or negative, and we're going to draw that delta from a Gaussian distribution. And you perturb it, and then you could imagine connecting this x0, y0 with this perturbed xm, ym, and then connecting it to x1, y1, and that will give you a little jiggle in your line. And since we're doing recursion, then what we're going to do is we're going to recur on the left and right intervals. And now this x0 becomes the left interval, and xm, ym becomes the right interval, and then that's one recursive call. And then the second recursive call is going to use the xm, ym as the left interval, and then the x1, y1 is the right part of the interval. And here's the Java code that does that. Here's the recursive function curve, and it takes the 2 initial endpoints, and then it also takes the variance of this Gaussian. So we need to compute this delta, and the delta is drawn from this bell-shaped Gaussian distribution, and the bigger our variance, the more that delta is going to move up and down. It's going to make it more of a jaggedy line, a more variable stock in the graph. Here's our base case. So remember, you must always have a base case. We see this is a recursive function that calls itself twice. We've got curve, and then curve calls itself twice, one on the left half and one on the right half. And here's it drawing that random delta value. All right, and we can go ahead and let me pull that up. We can run this in a Eclipse. Alright, so here's the same program in Eclipse, and we can see what I've got set for a okay, do I have a, oops, I'm on Plasma Cloud here. I want to be on Brownian. Still on. Alright, fine, we'll go up, fine Brownian, there we go. And let's set a variance of 0.1 and then we run it. Okay, and I put a little delay in it so you can kind of see it as it draws. There's a Brownian motion with that variance, and if we were to decrease the variance to 0.01 and then run it, it would tend to stay more towards the middle line, and we could lower it, you know, maybe 2 orders of magnitude, make it really small. And now it really doesn't like to move much off of that center line. Alright, so that's simulating Brownian motion just on a single line. I promised to show you how I made that cool graphic on the intro slide, and that's what's called a plasma cloud. It's pretty much the same idea as this thing that computes the Brownian motion. We're just going to randomly perturb something, but in this case we're working in 2 dimensions. And if you imagine we've got a square, alright, and each of the corners of the square have some color value, say in grayscale. We're going to divide that square into 4 subsquares and assign new grayscale values to all the new points. So these little dots, all 4 of these points need new values. These points on the outside are just simply going to get the average. This is just the average of the grayscale to the left and to the right, and this is the average up and down and so on. The only one that's interesting is this very center one. The center one is going to be the thing that randomly gets perturbed, again by a delta, and then we'll draw that delta from a distribution as well. And as you run this, you get different images. So here are some different runs I got from the Plasma Cloud program, and we can go ahead, I guess let's go ahead and oops, alright, and you can check out the Plasma Cloud code. You can see it here, it's drawing its displacement and then it's perturbing that. It's calculating the different points on each of the sides, and it's got this little get HSB color thing that's giving you, it's not just doing grayscale. Actually, we've got this cool you know, color scheme, and that's this thing here is doing that cool color scheme. And it's a recursive algorithm though, so Plasma is calling itself 4 times recursively on each of those coordinates of the box. And here's our base case up here. Always good to have a base case. As this size gets too small, then eventually we just stop the subdivision. So all good recursion must come to an end. And it initially just starts the 4 boxes at random colors. That's why every time we run it, we're going to get something different, because it's starting with different colors in those 4 corners. And let's go ahead and run Plasma Cloud, and you can see it. It takes a little while to generate this, but you can actually see the recursion working. It's starting in the lower left, then it's going lower right, then upper left, then upper right, and then working its way up. And so it kind of looks like maybe like an image loading, and getting less pixelated as it goes along. But it's actually calculating all these new values according to the algorithm I just described. And now it's working on the big lower right one. Alright, and we could keep watching that, or I'll show you another trick you can do. So I stopped it. If you want standard draw to draw really quickly, one thing you can do is call standard draw.show 0. And so actually painting those pixels to the screen is expensive. It can actually draw it a lot quicker if it just draws it to sort of a back buffer. So it doesn't actually draw it to the graphics hardware, it just draws it to memory. And if you call standard draw.show, what that does is this whole Plasma thing will keep calling and asking for things to be drawn, but it will never appear on your screen. It won't appear until you make another call to standard draw.show, and so it's important you got to call it afterwards. But by doing this bracketing, now I run it and it's instantaneous. Okay, and I can draw another one, and each time I get something different. plasma clouds. Here is same idea. Somebody developed this, so this kind of looks like a fjord in Norway or something, but in fact it's just a computer-generated landscape using some similar recursive algorithm that's randomly perturbing things and creating the hillsides and so on. Let's talk a little bit about divide and conquer. And this is very related to recursion, and I'm going to show you how to divide and conquer the sorting problem. The whole idea of divide and conquer, it stems, originally developed by Julius Caesar. So his favorite war tactic was to split the opponent, the opposition army, cut them in half somehow, split them up, and then fight one half with his full army, and then beat them, and then fight the other half with his full army, and then beat them. So divide and conquer, or I came, I saw, I conquered. Split it up, and then we normally solve each subproblem recursively and then combine the results in some way. And divide and conquer is a very common paradigm in computer science. You'll see it again and again if you carry on in computer science. And today I'm going to show you the merge sort algorithm, which is a way of very efficiently sorting a bunch of stuff. Divide and conquer is used in other domains, like how to parse programming languages. It's used in signal processing if we're doing multiplication of very large numbers, or eventually we'll talk about link structures. And so it's a very good way of handling things like graphs and lists of things. Here's the problem. We need to sort a bunch of cards. And let's sort them just by number. We'll ignore suit and we'll say that aces are high. How am I going to do this? Well, somebody gives me a big pile of unsorted cards. I'm going to divide and conquer. I'm going to split them in half, or as close as possible. So I might not be able to exactly split it in half. Okay, here, how many do I have? I got 9. So I'm going to have a pile of 5 and a pile of 4. It's as close as I can get. I'm going to give each half to somebody. And I'm going to tell both these, I'm going to give 5 cards to one person, 4 cards to the other person. I will just tell them to sort them, and then they give them back to me, and then I merge them. Alright, it's the ultimate in laziness. I don't want to sort them, so if I give 2 people the cards and have them sort them, then my job is quite easy. If I'm handed back a sorted pile, my first person gives me the pile on the left, and my second person gives me the pile on the right. So they've given me the, sort of in ascending order with the smallest card on top. How do I merge the cards? Well, pretty easy algorithm. I just look at the 2 cards that are on top and choose the one that's lowest. In this case, I take 2, right? Now that I've taken the 2 off, which one's the lowest? Well, 4 is the lowest. So again, I take it from sorted pile number 2. Now which one's the lowest? 7. Alright, so I take it off sorted pile 1, then sorted pile 1 again, and then sorted pile 1 again, and again. Now I've got a queen and a king. Queen wins. Sorted pile 1 is now out of cards, and so now I have no choice. I take from pile 2, and then again from pile 2. How many operations did it take me to merge those cards? As a function of the number of cards. So if we said we had 9 cards, and if we call that number n, how many operations did it take? Well, it took order n, so it's linear in the number of cards to do that merge. The merge is pretty easy to do as you saw. But of course, there's a fly in the ointment. Is how did pile 1 and pile 2 get sorted in the first place? I don't really have 2 people that that could sort them. I've actually got to get the computer to do it in some way. You may have guessed what the answer is, right? We'll just do it recursively. Somebody gives me, an unsorted pile. I just split it into 2 halves, and then whoever gets those 2 halves, everybody gets one of those halves, just splits their half up and gives it to 2 different people. And graphically, it looks something like this. Here's the top, a bunch of unsorted integers. You split it in half as close as you can come to splitting in half. This guy's only got 4 numbers to sort. He splits it into 2. and then splits it in again. So eventually you're going to get to just a single thing, and once you have a single integer or a single playing card, whatever, it's sorted. And then you can start merging, and 38 sorted is a sorted pile, 27 is a sorted pile. And how do you merge them? Well, you take the 20, whichever one's less, you take the 27 and then the 38, and then both piles are gone. And you take the 3 and then you take the 43, and then you have this pile, and then you merge these to get 3 and then 27 and 38 and 43, and then you work your way back up, and when you're all done, you've got a sorted list of numbers. Alright, and how many times do you have to split it? Well, if there are n things in this list of integers or cards, if you're dividing by 2 every time, then this is a log base 2 of n. Alright, log base 2 of the number of things, because every time it's cut in half. So that's how you get what I showed you, a few slides back. This is a very efficient sorting algorithm that operates in order n log n time. Alright, to summarize, we talked more today about recursion. Sometimes when you call yourself recursively, you just call yourself once, as is in the case with binary search. Sometimes you've got to call yourself twice, as in merge sort. And we saw other examples like plasma cloud or H-tree or brownian, where you call yourself, well, I guess brownian was twice, but plasma cloud called itself 4 times. Always remember, when you do recursion, it must end at some point, so be sure you have your base cases. And it's a very powerful tool in computer science, and one you're going to be seeing a lot of if you carry on in computer science.